This video is over the difference between linear and exponential functions. On your notebook, please write your title of linear versus exponential. We're just going to review linear since this is something we've worked with so far this year in several different aspects. All linear functions are written as f of x. My arrow there we go, are written as f of x equals mx plus b, where we know x is our inputs, f of x, or our y values, those are our outputs. Our b value represents y or initial value, kind of like what we start with. And we know that our m represents our slope or our rate of change. Remember, those words mean the same thing. Most recent example I can give for a linear function is the detention buyout task. For example, if we think of Mr. Bisson and his function for his detention buyout plan, it was f of x equals 105 plus 625x. And we know that this number here, that 625, that represents our slope because it said it costs 625 per detention. That's why it's next to the x. Because each detention x, we'd have to multiply by $6.25 plus the 105 initial value or y-intercept, because that's what he charged no matter what. Almost like that flat administrative fee that he talked about. Notice that when you did your tables for Mr. Bisson, that we saw an addition pattern there. Anytime we're working with linear functions, we're going to see addition or subtraction patterns. In this case, it was just addition, since every detention a student got, the price increased, which makes sense. If you get more detentions, the price you'll have to pay gets higher. Now, on Friday, we started talking about exponential functions, and the example that we looked at was the paper folding task. So we looked at a piece of paper with 0 folds in it. And when we had 0 folds in it, we said that the space, the number of sections of the paper was just 1. Well, when we folded, eraser's crazy. When we folded the paper one time, we noticed when we unfolded it, we had 2 sections. When we folded it twice, we had 4 sections. 3 times, we had 8 sections. 4 times, we had 16 sections, and so on and so forth. Some of you tried to fold the paper 7 or 8 times. That was our challenge from our Mythbusters video that we watched. But the idea behind this is that our linear pattern that we are used to looking at no longer works, because many of you said on Friday, you're like, wait a minute, this change, this is a, oh my goodness, come on. Sometimes my hand gets in the way there. All right, we noticed that the change was plus 1, but then this change was plus 2, and this change was plus 4, and everything is different. Our change is different. So we knew that our linear functions wouldn't be able to help us anymore. So that's where we came up with a different type of equation to help us, and we're going to define that further today. So exponentials, the function that we use is f of x equals a times b to the x power. In this case, exponentials mean to an x power. In this case, our base is some value, b, and a is our initial value, what we start with. But the key here is that exponential means it's to the x power. So again, let's review that. Our a is our y-intercept, or our initial value of what we start with. And if you remember with our paper folding task, we put in our equation that a was 1, because here with 0 folds, we had 1 section of paper. Now, our b, what that represents is our pattern in this case. Our pattern, okay? Or what we are multiplying by. What we multiply by. And that x, as just like in linear, that's our inputs. And f of x, of course, is our outputs in this case. So again, there are some similarities between the linear and the exponential, but of course, our exponential, those are our multiplication patterns. And some would say, yes, division patterns too, but if we're dividing by 2, that's the same thing as multiplying by a half. So just keep that in mind. So a quick example, if we want to look at another one, if we said we had x, I'm writing my table sideways here, and f of x, and we saw it was 0, 3, and 1, let's say 6, and then 2 times 2, we'll say 12, and then 3, 24, and then 4, 48, and so on. I'm noticing that my change isn't adding by the same amount every single time. It's doubling in a sense. So our equation in exponential form would start with f of x, and how I got that f of x, how I get that 3, is I take my first term, my y, my initial value, my y-intercept, which we know in this case is 0, 3. So we would put 3, what we start with, times my pattern. I notice my pattern is multiplying by 2. So it's 2 times 2 to the x power in this case. So it's almost a little bit simpler even to write than our linear patterns, because a lot of you instantly were saying, oh, I just see what I'm multiplying by. Now remember, this base does not always have to be a 2. I happen to do 2 different examples when the base was a 2, but if you notice the pattern's multiplying by 3 or 4 or 5, then this b value would be one of those. Now for your work session today, I'm going to give you a bunch of different scenarios, and I want you to tell me if it is a linear pattern, linear, or if it's exponential. And you'll kind of know the difference on if we're adding or subtracting, or if we're multiplying or, in a sense, dividing. You'll also try to write the equations for each one, and remember how we find slope and y-intercept for linear. We've got those posters on the wall, and then we just talked about how we would find it for our exponentials. So good luck. When you're done, take a picture of your notes with this, with your work, and upload it to Canvas. Thank you.